All right, so we were talking about on Friday, we were talking about applications of quadratic functions, right? And this was just this is an interesting intersection of abstract math and the real world, right? So we were looking at some problems that we were able to model with quadratic functions. And just quick review, remember that if we're starting with a quadratic function in standard form, ax squared plus bx plus c, and we want to graph the function, or we want to at least think about what the graph would look like, we know that the x and y coordinates of the vertex, h and k, are given to us by this little formula. H is negative b over 2a, and k is just f of h. We'll plug h into the function and see what we get. And that's going to give us the vertex. And then we know from the value of a, if a is positive, the parabola opens up. If it's negative, it opens down. And sometimes that's all the information we need to answer some what we call optimization problems in math, where we're trying to find minimum and maximum values of functions. Sometimes just knowing if it's a parabola, if it's a quadratic function, and then if the vertex represents a minimum or a maximum, sometimes that's all we have to do. And just remember, if the parabola opens up, if a is positive, then the vertex is a minimum. It's the lowest point on the function, and so it's the minimum value of the function. Whatever that function represents, it's the minimum value of that, right? For us, it was an area. It's the one we were working on. So maybe we want to minimize area. Let's see, what about if a is negative, then the function opens down and the vertex would be a maximum, right? Okay, so let's go back to the problem we were working on. It was this guy right here, and we were trying to maximize area, weren't we? So we said a person has 220 feet of fencing to enclose a rectangular garden. What dimensions of the rectangle would give the maximum area? Okay, and so what we were able to do here is we drew a picture. Here's our rectangular garden. We called the width of the garden x. And then we reasoned that I know that the area of a rectangle is just the width times the length, right? And we had to come up with an expression for the length then. Well, we knew that if the perimeter was 220 feet, then the distance halfway around the rectangle, so if as it's drawn here from the upper left to the bottom right, would just be half of the total perimeter. That's 110. And if the distance from there all the way down and across is 110, and the vertical width as it's drawn here is x, then how much is left over for the length? Well, that entire 110 minus the width x would give me the length, right? And so we came up with expressions then for the width and the length, both in terms of x. And so when I multiplied those together, the width times the length, x times 110 minus x, I got 110x minus x squared. If I wanted to write that, we could recognize that's a quadratic function in standard form if I just write it a little differently. If I put the x squared term first and the x term second, then it's matching my standard form of a quadratic function, right? And what do we say then? Well, we know that a would have to be -1. That's the coefficient of x squared. B is 110 because that's the coefficient of x. And there is no constant, so c is equal to 0, right? And then given that information, we're able to come up with the coordinates of a vertex, and that's where we sort of left off. But I wanted to just reinforce that we already know some stuff about this. We know that because a is negative, the parabola is going to open down, and so its vertex is going to represent a maximum, right? Because the vertex is the highest point on a parabola that opens down. And so if we're trying to find, what is the maximum, or what is the width that gives us a maximum, what's the value of x in this case, because x is width, what's the value of x that produces a maximum, all that stuff is going to be given to us by the coordinates of the vertex, right? Right? The vertex is the x coordinate of the vertex is going to be a value of x. The y coordinate is going to be a value of area. It's going to be a value of a. And I've just got this function. It works like any other function. If I plug in an x value, it's going to spit out an area, right? It's an a of x function. And where we left off is we just tried an example. What if I plug 10 in for x into my function? If I let x equal 10 and I plug that into my function a of x, well, look what I get. I get a value negative 10 squared is negative 100 plus 110 times 10. I'm plugging 10 in for x, gives me 1,000. And I could even use, for example, I could even use like Desmos to calculate a whole bunch of values here if I want to. Right? I could go into, let's do this. If I go into Desmos graphing, and let's ignore the graph even here for a second. What if I just, I'll just leave that part visible. We won't even see the graph. We don't even need to see the graph. But if I plug in the function, let's call this a of x instead of f of x, because it's an area. If a of x equals negative x squared plus 110x, and then there is no value for c, it's 0. I could go on to Desmos and I could calculate all kinds of values here, right? I could make a table out of this. If I could plug values in. I could do a of 10, for example, and it gives me 1,000 for my answer, doesn't it? I could go up here if I want to make a table out of this. Remember this trick? I could type the gear. I could hit the gear button, and I could convert this whole thing into a table, right? And then look, I get values for a bunch of different x values. It's giving me y values now. Now I don't really care about I don't want negative values. Negative values don't make sense for this. Don't make sense for this model because I can't have a negative width. Okay, but I can do positive values. 0 doesn't even make sense, does it? If the width is 0, the area is 0. That doesn't even make any sense. But look, as I pick values of x and plug them into my function, I'm just getting outputs that are areas. Everybody see this? Does that make sense? Okay, we left off on 10. 10 was 1,000, right? If I keep going with this, look, the areas keep climbing, don't they? Getting bigger and bigger and bigger. Keep going up. Look at that, they keep going up. Still going up. Still going up. Oh, they're going down. Suddenly they started going down. Look, if I pick all these widths, as the width got bigger, the output area got bigger until we got up here to, it looks like 55. 55 is where it's, that was the biggest output we got, and then it started to decrease after that. Okay? Huh. If I graph these points, let's see what this looks like if I graph these points. I'm going to have to zoom out a bunch, right? And I'm going to want to maybe, let's go ahead and practice setting our window. Didn't we do that once last week? Give me a thumbs up. Didn't we practice setting the window once last week? Did we not do that? Okay, never mind. Let's get a little practice. This doesn't look very good, does it? Right? If I want to look at this graph, and let's say we want to look at this graph, it doesn't look like a parabola to me, right? I can't see what I need to see on the graph. So let's go up here in Desmos. Let's go up to the gear, and we're going to set, scoot this thing over just a little bit here. We're going to set the window so we can see it better. Okay. Let's see. Let's look at the x-axis. Right now, x is greater than or equal to negative 22.11 and less than or equal to 303 point blah, blah, blah. Well, look what that means. The left edge of the screen that you can see is over here at about negative 22, and the right edge of the screen has an x value of about 303. Do I need that wide a range of x values? Does my domain that I'm looking at need to be that big for me to see this parabola? No, look, it looks like this parabola has x-intercepts at 0 and 110, right? So why don't I go back and I'm going to change I'm going to change the X settings. So I'm going to go over here and I'm going to hit Control A to highlight the number that X is greater than, right? So that's the left edge of the screen. And why don't I just do something like, I'm just going to make it a small negative number. Like how about something like negative 10? Okay. What about the top number? If I tab over to the value that X has to be less than, right? The top edge of my interval, which is the right edge of the screen, 110 was my X-intercept, so why don't I just do something like 120? Well, look what that did. That's good. Now, horizontally, I've spread this thing out, so I don't need it to be any wider. I'm trying to spread the graph out so it looks big on the screen. Okay, but now I don't see the vertex, right? I need to see the vertex. So pretend I don't know how high the vertex is. I'm just going to go into my graph settings, go down to the y-axis, and I'm just going to mess around with this thing until I get a value that works for the top value. What if I tried something like, 400? That's not big enough. Okay, so maybe I have to make it a little bigger. Let's try something like 1,000. Still not big enough. Let's try something like 2,000. Still not big enough. 3,000, still not big enough. Let's try something like 4,000. There, finally I can see this thing okay, right? And now I can just pick the thing up a little bit, and now I can see my graph. Everybody get that? Okay, and here's all these points that I've graphed. Do I need all those things? Nah, probably not. Probably not. If I click on the graph now, it's going to highlight the x-intercepts, and look, the vertex. It knows I might want the vertex, and so I'm able to just click on that point, and it gives me the coordinates of the vertex, right? Okay, so there's a little bit, it takes a little practice to get these things, these graphs so you can see them really well. Do they have to be picture perfect every time? No, they don't. They don't have to be picture perfect, but if I start off with my regular home screen and I just zoom out until I can see this thing, that's kind of, that works, but it's kind of an awkward parabola to look at, right? It looks pretty skinny. I can still get the same information, right? But it'd be easy for me now to just go back and maybe tweak this thing so the x-axis is spread out a little bit so it looks more like a regular parabola instead of this tall, skinny thing, right? Everybody give me a 1 to 5. Does it make sense? Does that kind of give you just a little sense of when you're trying to use something like Desmos or a graphing calculator, could be a TI-84, how you can go, you can set the window so you can see the graph better, okay? All right, so let's go back to where we had this thing. We had it looking really nice. There it is, okay? All right, so how could we do this without the benefit of a graphing calculator, right? We just need to find the coordinates of the vertex. Well, we know what those are. Those are just h and k, and we have our formulas for finding h and k, right? We know that h is equal to negative b over 2a, right? So I know what a, b, and c are. There's my values of a, b, and c. If h equals negative b over 2a, well, b is 110, so negative b is negative 110. A is negative 1, so 2a is negative 2, so h is negative 110 divided by negative 2. Negative over negative is positive, and half of 110 is 55, right? So we know that the x-coordinate of the vertex is 55. Okay, what about the y-coordinate? Well, then that's where I'd have to just plug that value back into my function. So k would just be f, but it's not f in this case, it's actually a, isn't it? Instead of saying f of h, it's going to be a of h, because our function up here is, we defined it as a of x, not f of x, a for area, right? So we get a of 55, which is just going to give me, if I look at my function up here, I'm going to get negative whatever my input is squared. Well, that's 55 plus 110 times my input of 55. So negative 55 squared plus 110 times 55, that's the same as 55 squared, which is 3025. Okay, so then we end up with the y-coordinate of the vertex is 3025. So we found the coordinates of the vertex. Now, how do we interpret that stuff? What's the 55 mean? Well, 55 is a value of x, right? Everybody agree this is the x-axis, and so this is a value of x. Looking at our picture up here, x is the width, right? So what's that 55 mean? It means that the width equals 55 feet. Everybody give me a 1 to 5. Does that make sense? When we find the coordinates of the vertex, we found the maximum, which is what we're looking for. And what do the coordinates tell me about the maximum? The width is 55 feet. Okay? Right? How about the other part of it? What does the 3025 tell us? Well, the 3025, the output is an area, right? That the y-coordinate here is, y corresponds to a of x. So that means that the area equals 3025 square feet, because we measure area in square feet. Okay, give me a 1 to 5 on that. Okay, that's pretty cool what we just did, right? What we just did there, because we recognize this is once again where we get that intersection of just totally abstract math and the real world, right? We've got this function that we built that models area as a function of width, and because that is a quadratic function in standard form, we know it opens down and we can calculate the coordinates of the vertex really easily, right? Using our little formula, negative b over 2a to find h and plug it in to find k. And so we know, we don't have to know anything else about this function. We know that the maximum is going to occur for this area function when the width is 55 feet and the biggest value the area could ever be is 3025. So what's that tell us then? Well, it tells us, oh, whoops, didn't want to do that. It tells us that the width has to be 55, right? The maximum area we calculated is 3025 square feet. And what's the length? Well, if we look at our picture right here, if x is 55, I could plug 55 in right there, couldn't I? Right? If I know that x is 55, if I plug that 55 in right here, 110 minus 55 gives me my length. Well, that's just 55, isn't it? Man, can't get it right here today. So the length is also 55 feet. Which, in hindsight, they always say hindsight's 20/20. That probably makes sense, doesn't it? Wouldn't you kind of anticipate that if you want to make the biggest garden you could, that's a rectangular garden, and I had 220 feet of fencing, wouldn't it kind of make sense that you'd make a square to enclose the most area, right? That's what we just showed. Okay, let's look at one more example of this. How about this one? Another example here. Okay, this time, what are we trying to do here? We're trying to make a rain gutter, right? So we make rain gutters out of sheets of aluminum, long rectangular sheets of aluminum, and then we just bend up the edges to make a trough. That's all we do, right? So we start off with these long sheets of aluminum that are 18 inches wide. And so if we want to give this thing a little perspective, it just looks like this, right? Right, so if I want to give this thing a little perspective, like there's the front edge, and I've got this long sheet. that's kind of disappearing into the distance, right? Here's the front edge. And if, let's say this thing has some lines on it, the lines are just going to look kind of like that, right? It's just going to go. Everybody get that? There's my perspective drawing. So this is the front edge and that's the back edge a long ways away. Okay, what I'm going to do, does everybody see what that looks like? Just my not very good example of a perspective drawing. Okay. So now I'm just going to bend the edges of this long piece of aluminum up to create a trough that the water can flow through, right? And so let's label this. We don't know, we're trying to figure out how far do I bend up the edges to transport the most water, right? Well, it turns out, and this makes sense, doesn't it, that I just want to create the biggest possible cross-sectional area there. I want the rectangle that's going to represent the water flowing down this thing when it's totally full of water. I want to have the biggest area possible of water that's flowing down this trough. Everybody agree? When we say something like a cross-section, you know what that means? What's a like if I took the cross-section of the trunk of a tree, what shape would it be? If I look at the cross section of the trunk of a tree, yeah, it'd be a circle, wouldn't it? Right? In other words, if I cut through the trunk of a tree, what does the cut look like? It'd be a circular cut, wouldn't it? Right? So here, we're going to bend up the sides. So if I've got water flowing down this, I've got water flowing down through this trough, the water is going to make a rectangular shape, right? I've got this, like pretend I froze the water into a block of ice and I cut through the ice. Well, wouldn't I just get a rectangular cross section to the water in the gutter then? Okay. We want the area, we know that we can transport the most water, the largest volume of water through our trough if that cross-sectional area is the biggest it could possibly be, right? Okay, so we don't know what the depth of the gutter should be. That's what we're trying to find. So we're going to call that X, right? The height of this thing is going to be X, or the depth of the trough, let's say, is going to be X. Okay, and if I draw a picture of this again, here's kind of what my trough looks like then. I've got this. Everybody agree that's my trough when okay, receding into the distance. Okay, so I need to know though, I want to be able to calculate the area of this cross section. Well, just like before, you already told me that the area of a rectangle is just length times width, or in this case, depth times width, right? This cross section of the gutter, the area of the cross section is going to be the depth of the gutter times the width of the gutter. Well, what's the width of the gutter going to be? If we built this thing by bending up the edges of an 18-inch wide piece of aluminum, type in chat for me, how could I write down the width of this gutter then? What's the width of the gutter going to be? The width of the piece of aluminum that we used to bend the gutter was 18 inches. So what's the width of the gutter going to be after I make those bends to create the trough? What do you think? Still waiting for some answers. We said that the depth we were going to call X. That's an unknown, so we have to call it a variable, right? Because we don't know what the value of the depth is yet. because I want to calculate area here, right? So my area is going to be x times what? I need the depth times the width. I got to know what to multiply x by. Okay, we're getting there. We're getting there. So it's like I'm going to put my bends. Let's say that this distance right here, if that's x, I'm going to crease the thing right there, and I'm going to fold that part up. And I'm also going to have to do the same thing on this side, aren't I? If that distance is x, I'm going to have to bend this side up by x also. So there's my crease. And I'm going to bend that side up, and I'm going to bend that side up. So what's left on the bottom then? Some people said 18 minus x. Is that right? What if x happens to be like 4, for example? Let's just say hypothetically that we want the depth to be 4 inches. If I bend each of these tabs up to be 4, what's the width going to be? Is it going to be 14? 18 minus 4? Right? Let's just say I created a gutter. This may not be the right one, but if that's 4 inches and that's 4 inches, how wide would the gutter be? Type it in for me, please. It'd be 10, wouldn't it? Yeah. Right? Because the whole thing has to add up to 18, right? Well, I don't know that it's 4. I called it x. So what's that width going to have to be? Okay. I see a correct answer up there. Can anybody identify what it is in the chat? There we go. Yeah, it's 18 minus 2x, isn't it? Because I've got to subtract that x and that x from my total of 18. Okay, good. So then I know that my area is going to be x times 18 minus 2x. That's my cross-sectional area, isn't it? Now look, I've only got one kind of input, x. So I could call that function a of x if I want to, right? Because I'm inputting x's. That's the only thing I need to input to make my calculation of my output area, right? And this looks an awful lot like the last example we did. If I distribute that x, would everybody agree? If I distribute, I'm going to get 18x minus 2x squared, and I can rewrite that to make it look like a quadratic function in standard form. If I just put the x squared term first, now that looks like ax squared plus bx plus c, doesn't it? Right? So what are the values then? You tell me. What are the values here for this function? Type it in chat, please. What are the values of, let's not confuse the a's. This is our little a, right? Not our capital A for area, but just our regular old little a for standard form. What are the values of A, B, and C? Type those in chat for me, please. Okay, good. Yeah, so we get -2 for A, that's the coefficient of x squared. We get 18 for B, that's the coefficient of x, and there is no constant, so C is equal to 0. Okay, so if I've got A, B, and C, I should be able to calculate the coordinates of the vertex pretty easily, right? We know the formula. H equals -B over 2A. So what's that going to give me? If I plug in, if B is 18, then -B is -18 divided by 2 times A is -2. 2 times -2 is -4. Negative over negative is positive. And if I divide 18 divided by 4, I'm just going to get 4.5, right? That reduces to 9 halves. we'll just write it as a decimal. That's just 4.5 is my value of h, right? Okay, so that's useful. If I were going to make a graph, or think of this in terms of a graph, so x is my input, that's my horizontal variable. The input is always the horizontal variable, and my y value in this case, well, y, we're replacing with a of x. That's my output. So that's area. Well, I know one thing. I know that my x-coordinate of the vertex is going to fall halfway between 4 and 5, so 4.5 inches. If I want to calculate the output, I'm just going to plug 4.5 into my function. And let's use Desmos for that, right? We can use Desmos to make that calculation. So remember how we use Desmos here. I'm going to type in, and I shouldn't say F, I should say A, shouldn't I? Whoops. Not that it makes that big of a difference. But my function is A of x, not F of x, right? So let's make that one little change. So K is going to be A of H, which is 4.5, okay? So in Desmos, I'm just going to define my function, first of all, right? So I've got A of x. Remember this trick? This is so useful. A of x equals negative 2x squared plus 18x. And then I'll just go down to the next row and I'll evaluate my function at 4.5. Look what I get, 40.5 for my answer. And you have access to Desmos, the scientific Desmos, and that's all I'm using. It's not even the graphing one. You have access to that all the time on tests, right? So you can use Desmos for this stuff. Oops, right there, that's what I want. So A of 4.5, we already found the value of K then. It's equal to 40.5. And so let's say I'm going to change the scale on this. We'll go up by tens. There's 10, 20, 30, 40, 50. So I've got my vertex at 4.5, 40.5, so right up about there. Does this parabola open up or down? Give me a U or a D in chat, please. Should hear from everybody. Okay, yeah, A is negative, so you know it opens down. So we got it, right? We got it. We know. We're trying to find a maximum for volume, right? Well, maximum for cross-sectional area, so we can maximize the water flow, right? And so what does this tell us then? What do the coordinates of the vertex tell us? Well, the 4.5 tells us that the depth equals 4.5 inches, right? And the 40.5 is telling us that the cross-sectional area equals 40.5 square inches. We don't really care about that, though. The question didn't ask for that. It just wanted to know what's going to be the depth of the gutter that's going to maximize the cross-sectional area. So there it is. It's 4.5. We got it. right? It's just going to be the x coordinate of that vertex. That's pretty cool. How else are you going to do that problem, right? I mean, I guess you could argue maybe you could go down and make a table in Desmos, but if I make a table in Desmos, look what happens. It doesn't even work this time very well. So here's my table in Desmos, right? I got to change my function this time. So this time it's negative 2x squared plus 18x. Oh, that's going to take forever. If I recreate, oh, there we go. Good. So look, I could make my table and I could, oh, look what happened. When I make my table, I didn't get a single value that gave me a maximum, right? And how do I know that every time that that my maximum is going to work out to be something convenient? It might be some bizarre decimal that's not going to, that's I'm not going to find using my table, right? So the table is useful sometimes, but really, I mean, if I didn't, in this case, it might not be much use at all. I guess I could reason that because those are even, I get the same outputs at 4 and 5, I could average the two. You could maybe think of it that way. But it's easier just to find the vertex directly, right? I know I've got this downward opening parabola. Just find the coordinates of the vertex, and that represents a maximum because my parabola opens down, right? And the only reason that works in this case is because the function that we built for area happens to be a quadratic function in standard form. If it had been a different kind of function, we would have had to approach this problem differently, and we'd need a little bit of different math for it. But we're talking about quadratic functions. And so in this case, we ended up getting an area function that's quadratic, and so we know how to deal with it, okay? And it's, I know it's easy to get lost in just the fact that this is just another word problem on an assignment, but try to think beyond that a little bit and just try to see the beauty in that. That's pretty cool that we can take this abstract math concept that seems to have nothing to do with reality, and we can recognize that there's a parallel there, right? It's for some reason the math gods chose to represent this cross-sectional area with a quadratic function, right? And so we can use that fact to our advantage. Okay, everybody give me a 1 to 5 on this process. Is it getting a little better? Okay. All right. I'm going to make this. I want to give you guys a little bit of chance to work here, and we're running. Oh man, we're running out of time. I just want to show you something really quick. I'm going to make this super quick because I didn't mean for this one to go so long today. What if they give us a function like this, where this is a cost function? They're telling us the cost in millions of dollars for a company to manufacture X thousand automobiles. So they're defining what this function means. X is our input, and X represents the number of thousands of cars that your company is building. C is the output, and that represents the cost of manufacturing in millions of dollars. We want to find the number of automobiles that must be produced to minimize the cost. Well, would everybody agree here this is a quadratic function in standard form, and A is positive? So everybody see that this parabola is going to open up, isn't it? This is a quadratic function, so the graph is a parabola. And because it opens up, the vertex is going to be a minimum value, which is what we're looking for, right? We want the minimum cost. So all we'd have to do, and let's just cheat and use Desmos on this one to make it quick. I mean, we could go about this doing the, calculating H and K like we've done in the last couple examples. But let's say that this time we have Desmos graphing available. Okay, so let's graph this thing. We have C of X is equal to 4x squared minus 24x plus 72. Okay, and I can, if I just zoom out a little bit from my home screen, I can see, I'm not going to make this parabola look really good here. I can see that it is a parabola that opens up, and I can see the coordinates of the vertex are 336, right? That tells me everything I need to know, doesn't it? What does that 336 tell me? It says find the number of automobiles that must be produced to minimize the cost. What's my answer going to be? Blank cars minimizes costs for my company. Type your answer in chat. How many? Type your answer in chat. How many cars? You're the CEO of this car company. You got to make a decision here. How many cars should you target to build if you want to minimize costs, which is important? There's a graph of our cost function. Okay, when I make my graph here, you just got to always think in terms of the graph. If I'm graphing this thing, what do the axes represent? What's my input for my C function? What's the input? What variable is the input variable? Type it in chat. What's the input variable? Here's my function right here, right? Or right here. What's my input variable? Is it X or C? It's X, isn't it? Good. So X is my input, right? So this is the x-axis. The horizontal is the x-axis, horizontal axis. My output is C, and so the output is the vertical axis. My y-axis is charting total cost, right? So A is positive, so I know that this function is going to open up, which it does. And if I look at the coordinates of the vertex, what's the 3 telling me? It's telling me that 3,000 cars, right? Because we're talking about X is thousands of automobiles. So it's telling me that 3,000 cars minimizes cost. And what is my cost? My minimum cost is $36 million. So the answer actually isn't 36. The answer is 3,000. They wanted to know how many cars should we produce to minimize costs. They never actually asked us what the minimum costs were. They just wanted to know how many cars should we build? 3,000, right? Because that's the input value. That's the value of H, the X coordinate of the vertex. Everybody get that? Okay. All right. Well, you got no time to work today. Sorry about that. I'll try to work in some time. Maybe next time. Next time I'll work in some work time for you. Okay. All right. Have a great day. I'll be here after school if you need any assistance with anything, but this should get you going. Really, all this was about the last 2 questions on 3.4. Okay, so just wrap up 3.4. Next time we'll cover 3.5, and then I'll put a review assignment up. So it'll be next week we'll be doing our test. Okay, I'll let you get out of here early. Have a great day.